Hello, welcome to the sixth lecture of this course. And in today's lecture, we are going to do something quite exciting. We are going to write a program which will apply all the abstract data type features that we have designed and implemented. Some of the stuff that we have designed earlier, we've not yet completed the implementation, though we have completed discussing it. So in today's lecture, we will go through this implementation in detail and then go through the programming exercise that is going to use this abstract data type. And I'll encourage you to focus on the programming practices also. What I mean by programming practices is how do you decompose or break down a single programming exercise into smaller manageable components. Most important thing is manageable components. Somebody else who wants to develop your uh, program and take it forward should be able to do so. It must be appropriately documented and it must also be appropriately split into smaller manageable modules. Those are the things that we will really not talk about, but by looking at my presentation, you should be able to get an idea of how to achieve these things. That is the focus of this lecture. I also have some comments about the queries that people have been raising on the forums. So with respect to the programming assignments, so to the best of our knowledge, we can safely say that there are no uh, major errors with the compilers which you get access to when you submit your assignments. So these are uh, well tested compilers, so you don't have to worry about whether the compiler is making a mistake. So if your submission is not being successful, then you might want to look at your implementation and and understand how you are probably reading from the input and whether you're using the right algorithm, so and right problem solving technique. But please do continue to post on the forum, and we will try to answer them to the best of our abilities. All right, now let's go to the presentation. The presentation is going to be short, but a large amount of this lecture is going to go through a C program file, and it's likely that the lecture is going to be very detailed and intricate. So now let's go to the presentation. All right, so let's complete the implementation of the list data type. So in the last class, we essentially implemented the generic methods, the query methods, and the accessor methods. And here are the methods where we want to replace a certain element in the list with another value, right? Or exchange the contents of two positions in the list, insert an element before a certain position in the list, insert an element after a position in the list, insert an element to the first so that it becomes the first position in the list, and then insert an element into the last position in the list, and to remove a certain position itself. These are the update methods which we did not implement when we met during the last lecture, and today we will complete this. All right, so now let's now go to the program, and before we go to the program, I recall what are all the three main files that we edited and created to implement this abstract data type. Right? So when you create and implement an abstract data type, you're essentially creating a collection of files, and somehow a programmer who wants to use these abstract data type should be able to include these files. Right? So this is the most important thing. Another thing that we did not do in the last lecture was that we did not compile the list methods.c file that I promised to compile. That was an oversight, and we will definitely start with that today. And after that, we will look at a programming exercise when we come back to the come back to the exercise, come back to the lecture again. So now let's go to the so recall that this file was the file that contains all the methods associated with the abstract data type list, and the type definition, the most important type definition, is inside this file called list.h. So as you can see, I'm intending to separate the definition of the type or the creation of the new type from the methods. It's not a bad programming practice either to put all the methods inside this file, but if your data type itself gets very large, it's a good idea to separate these two. So now let's go to the list methods.c. This contains all the methods which are important for a programmer to use the abstract data type list. Okay, so we've included list.h and we have included the stdio.h. Like I said in the last lecture, it's most likely useless for us. And stdlib.h will be important because we will be using constants associated with pointers which are defined inside this library. For example, null is one such constant that we will repeatedly use. All right, so we've already seen the functions size. Right? Size takes in is intended to take in a pointer to the first element of the list and return an integer value which will represent the size of the list. Remember that this was a recursive function. Then recall that isEmpty is a Boolean function. It's a function that returns a Boolean value. In this case, it is modeled as an integer return value, and it says whether the list is empty or not. And observe that in the implementation, we ensure that the return value is either a 1 or 0. So it's up to you to just carefully return appropriate values, but the data type is an integer. So let me ask you a question. Would you be happy with such an implementation? Because a Boolean value is a single bit, but an integer uses close to 4 bytes. Uses 4 bytes or 2 bytes, right? So it's just a thought. I'm not giving you a solution, but definitely a kind of question that you should be asking. Then isFirst is another Boolean function which recognizes if a position is the first element of the list or the second element or not. Similarly, isLast returns if a position is the first element, if position is the last element of a list or not. So those were all queries to which the responses were of the Boolean data type. So now let's look at some queries which return objects of the node data type itself. The first function takes in a list and returns a pointer to the first element of the list. And the last function returns a pointer to the last element in a given list. Before returns a pointer to the node position just before a given position in a given list. After returns a pointer to a position just after a given position in a given list. And now we come to the update methods. Right? So these were the methods that we did not really talk about in the last lecture. So let's look at these update methods. Okay. So replace element is an update method. It does not return any value. Okay. And therefore, one has to be careful in making this function call. Okay. So it takes in 2 arguments. The first argument is a position in a list. Okay. And it takes in a key. And if the position is not null, it updates the value of the position with the key. Otherwise, it just returns. So I repeat, If position is not null, it updates the value, right, with the given value key, and then it returns. If position was indeed null, then it returns without doing anything. So such things, a program or a function that calls this method should be very careful to check that position has a meaningful value. Swap element is a well-studied function by most C programming students or programming students. Here, the two arguments to swap elements are the addresses of two positions, position 1 and position 2, and the result of this function execution is that the values in these two positions are exchanged. Okay? And again, we do not return any value from this particular function. Okay? Again, this function, any such function which does not return a value must be used very meaningfully, and it must be ensured that the calling function does all sanity checks on the parameters. That is, you must ensure that position is not null, right? And position 2 is not null, and so on and so forth. These are things that we are not checking for inside this function. Of course, one can definitely check here, right? And I will do this for you. If position 1 is equal to null, or right, so this one says that if either of the two is null, then you return. Right? But again, one has to be careful. There is no message that comes from this function that that this function call was meaningless, and therefore the execution of the calling function may get impacted if such meaningless function calls are made. So it is up to the programmer to ensure that the function calls that call swap element have meaningful arguments. This is going to be true for every method that you see in this implementation, and in general, this will be true for any function call that you make to a library of functions. I repeat this. It is important as a programmer for you to check that the arguments that you give to a function, okay, are always checked for their meaningfulness before the function call is made. Of course, there are well-written functions which may give you reasonable indication that an erroneous behavior has happened while execution, and the execution can update itself appropriately, not the program. Right? The execution itself can update based on the result of a certain function call. But it's a good programming practice to ensure that the arguments are sanitized before function calls are made. Okay. Having pointed out, let's move on and let's look at the other functions. By the way, observe that the implementation of the swap element function is fairly straightforward. We have an integer variable called temp. Temps is a temporary location that stores one of the two values. In this case, it stores the value of position 1. Then it affects the exchange. Most importantly, observe that we did not exchange the two positions, but we exchanged only their values. Insert before is very interesting, and among all the functions, this is the one that can be improved significantly. Okay. So what is the result of insert before? The result of insert before is a pointer. Okay. It's a pointer to a position which occurs just before which is inserted just before the given position in the list. In the value in the returned position is the value that has been given. Okay, so let me repeat this again. The result of insert before is an insertion. What is inserted? A node is inserted. Where is it inserted? It is inserted just before the given position in the given list. And in this position, the value that you see is the value which has been given as an argument to this function. This is the behavior of the insert before function. Okay. So let us look at the logic of what we would do. So let us assume that list points to the first element of the list. Now what we do is we find the predecessor of position in this list and insert the new value into a new position between the predecessor and the given position. I repeat this. In the list, assuming that the value list points to the first element of this list, we first find the predecessor of the given position. Okay? That is in the list, which is the node which occurs just before position. Then we create a new node, insert that new node between the predecessor and the given position, and assign the value into that position as the given value. This is the approach. So let's just quickly go through this piece of code. First, we check that the position is not null. Right? If the position is null, then you just return null, saying that, well, the query is not meaningful. Because the query is meaningful, which means position is meaningful, okay, we create a new node, we allocate space for a new node, and we call it new node itself. Then inside new node, in the value field, we put in the value that has been passed as an argument. Then recall our before function. What does before do? Before takes two arguments. It takes the list, it takes a position, and then it returns a pointer to the predecessor of position in the list. That is stored in this variable called prev. Prev is a short form for previous. And now we check if previous is null. What does previous being null mean? It means that position is the first element of the list. Right? That is, position is the first element of the list as it does not have a predecessor. So if previous is null, then recall from the before function that the return values are null only if position is the first element of the list, because the first element of the list does not have a predecessor. Right? Okay. Now let us just check this. Let's do one more meaningful check, right? So to handle erroneous function calls is really not necessary. Right? If one is going to make function calls very carefully, right? We first check if position is the first element of the list. Why are we doing this here? We found that position does not have a predecessor, and which means it must be the first element of the list. So now we check if indeed position is the first element of the list. What are we checking? We are checking if the function call is a meaningful function call or a meaningless function call. If it turns out that position is not the first element of the list, then we say, look, something is wrong with this function call, and we return a null. That we will not attempt to do this insert, we just return a null. Okay, so this is essentially to handle one type of an erroneous function call. We don't know how many erroneous function calls people can make. Right? We can't check for all of them. But definitely this seems to be a reasonable kind of error to make, and we are catching that. Okay. Now, if indeed position is the first element of the list, then we introduce the new node, right, as the first element of the list. Let us see what we do. Look at this statement. We say new node pointer.next is position, and we return new node. So let us see what has happened. We insert new node into the list, and here we insert new node as the first element of the list, right? And then we connect it to the rest of the list by making it point to position, and then we return a pointer to new node. Okay. On the other hand, if previous is not equal to null, right? That is what we do here. If previous is not equal to null, that means that the position has a predecessor, right? So now what do? The predecessor, now recall, is called previous, prev. We make previous point to new node, that is previous pointer.next is going to, previous pointer.next points to new node, and new node pointer.next points to position. In essence, we are inserting new node into the position between previous and the given position. Right? Therefore, the new node is now inserted into the list and the list is now longer, and we return a pointer to new node. This completes the procedure or the method which is insert before. Right? And then in this, observe that we have tried to handle errors that are common errors that people might make. Similarly, let's go to the next function, which is insert after. Right? Insert after takes as argument a list, a position in the list, right? And then a value. Right? Now, like previous, we say following. Right? The logic is very simple. What we will do is we will find the successor of position in the list, create a node, right, and insert it between position and its successor, and the created node will contain the value that has been passed. Right? That is the whole idea. So following stands for the successor node of position. New node is will be a pointer to a new node that we will create. Right? Now if position is null, you just return. Okay, as the lecture is going on, you may hear students in the corridor, so I hope that doesn't get recorded, but it's okay. So now here we create a new node, okay. We assign the value appropriately. Okay. Now here we compute the successor of position in list. Okay. Now if following is null, let us understand what this means. If position does not have a successor, then it means that it is the last element of list. Okay. Of course, observe here that we have not done any sanity check, right, as to whether position is actually inside the list or not. Okay. Fine, so that we should have done, but we are assuming that you can augment this code in such a way that it is clear. For example, it is important to check that this is a meaningful function call. We are not doing it here. So if following is null, then it means that position is the last element of the list. So we make position pointed or next to be new node. Right? And then return. So there is a small error here, right? I should have already said new node pointer dot next. This is a good programming practice. So this error was introduced deliberately so that you see this, observe what happened. This was missing, right? Fine. So what did I do? I made position pointer dot next point to new node, and I had not done something very important, right? I should have said new node pointer dot next is now null, right? If I did not do this, then the behavior of the program, right, may not be predictable, right? So therefore, we add this and then return. Okay? So, and you return. Observe that here we are not returning any pointer, right? We are just inserting. We are just inserting after a particular node into the list. Okay? And you can think about why. Insert before I return a pointer, but insert after I am designing it slightly differently and not returning a value. You should think about it. Right? I can also tell you, but maybe you should think about it, and then if you don't get it, you can ask on the forums and we will respond. Okay. If following is not equal to null, then it means that the successor of position is not the last element of the list. So now we have to insert the new node between following and its successor. That is what we do. Okay. So we say new node pointer dot next is the successor, which is called following, and position pointer dot next is new node. In essence, new node has been inserted between position and its successor. This completes the insertion of a particular node into the list. It can be insert before a position or insert after a position. Okay. There are two simple functions that are very important but now can be immediately implemented. This is insert first, right, into a list a given value. How do we do this? Okay. We just say insert before in the list first, before first insert a value. Right? So let me say this again. Insert first is very simple. You want to insert a node with the given value and make it the first element of the list. This is the goal of insert first. The way we achieve this is by making a function call to insert before. Right? What would be the arguments? Remember the insert before arguments, the first one is a list, the second one is a position, and the third one is a value. So I say insert before in the first insert in the list called first, before the first element, insert value. Remember that the return value is a pointer and you return that pointer. Right? Again, this function call must be used very carefully because the calling function must ensure that first is the first element of a list. Right? And if it is not, the programmer should have a clear understanding of what he or she is doing. Okay, insert last does the same thing but to the last element. So what does it do? It takes a list and inserts a new node with a value which is passed here and makes it the last element of the list. How is this done? First you perform insert after into the list after the last element of the list. Right? Remember that last is a function that we have already written. Right? After the last element of the list and populate it with the given value and then you return from here. Right. All right. So finally we come to a very important function which is to eliminate from the given list a position. Okay. So how are we going to eliminate? Right? So let us just visualize this. If you want to eliminate an element, if you want to eliminate a position from the list, you have to ensure that the list structure is respected. Right? So which means if you remove a certain position, you have to ensure that the predecessor and successor of this position are now predecessor and successor of each other. So this must be ensured. So to do this, we have two local variables called predecessor and successor. It's a pointer. These are pointers to node. Predecessor is a pointer to the node which is before position in the list. Successor is a pointer to the node which is after position in the list. Okay, it's quite possible that predecessor and successor are both null, right? Or at least one of them is a null. So let us see what we should do. Okay, if predecessor is a null, then it means that you are shortening the list by eliminating the first element of the list. Let us see what we are doing. If predecessor is null, right? So if predecessor is null, right, then it means that position doesn't have a predecessor, which means you're removing position. You're removing the first element of the list. So you free position, right? So this is a function call that you must definitely use as a discipline that every programmer should follow. Right? So when you are going to remove a certain dynamically allocated memory location, that is anything that you have allocated using malloc, it is a good programming practice to free it, right? Or rather, it is a responsible programming practice to free it, so that other programs or other functions can successfully run, right, and not fail because of the lack of memory. Then you return a pointer to the successor node. Right? Now if successor is null, then it means that the position is the last element of the list So what we do is we make the predecessor pointer.next is equal to null, and you have to observe that there is some very careful programming that has happened here. Right? I'll just come to that in a minute. Then you free position and then you return predecessor. So let us just see this. Right? So for example, first we compute predecessor and successor. Right? Let us look at the case where position, the list just has only one element, which is position, which means both predecessor and successor are null. Right? So if the predecessor is null, you free position and you return successor, which is null. And observe that this is very carefully done by not putting the successor check first. Right? Let us imagine what would have happened to the execution if this piece of code, right, was done before this piece of code. Let us see what happens. And let us consider the case when position was a single node. Right? Okay. So if position is a single node, then it means predecessor and successor are null. Okay. So if we were doing this comparison first and executing this piece of code, then successor is null. And observe the first statement. You say if predecessor pointer.next is equal to null. Sorry, we assign to predecessor pointer.next the value null, but predecessor itself is null. So this statement will fail if this piece of code was placed before the check which is involving predecessor is equal to null. Right? So this is what I meant by saying that some careful programming has happened here. So you must be aware of such details, or you must be checking for such details when you write pieces of code. You must imagine what happens during the computation. Anyway, okay, after ensuring the predecessor pointer.next is null, you remove position, you free position, and then return a pointer to the last element of the list. Okay, and if control comes to this location, it means that position has both predecessor and successor. So what you need to do is make predecessor pointer.next as successor, shorten the list by removing position, but don't break the list structure. Free position and return predecessor. So this completes the set of methods that we have implemented with the abstract data type. Observe that we have not given a function to create a list. This is for a person who wants to use this data type. He or she creates a list using these methods. Right? And that is what we are going to do, right, in the programming exercise. I hope you appreciate what we have done so far. So what we have been doing is that we have looked at the abstract data type list, right, and we have implemented a whole set of methods which are associated with this particular abstract data type. And very importantly, we've created the data type. So from now on, if you want to visualize the data type, one is the abstract definition, and if you visualize the implementation, you have to look at 3 files. Right? One file is a list.h, which defines the type definition, which is important. The second file is a list methods.c, which has all the method definitions that are relevant. The third one is a list interface.h, which is what programmers who want to use this data type will include and use this particular data type. So now, okay, again, I've forgotten to show you the compilation. Let's just go back and look at the compilation. Okay, so now what I'm going to do is I'm going to compile this list methods.c. The reason I am showing you this compilation is that recall that in list methods.c there is no main function. So many of you might think, or at least I have seen some people who think that you can compile C programs only if they have a main function. Right? So my answer to you is that no, that's not correct. Let us just see this. GCC minus C list methods.c compiles list methods.c and generates a object file. Okay, there are some errors here. Alright, so now I fixed those errors. Let me just show you the error that I made, right? So it is also interesting, right? Observe that what I did was I used the English word or, right? So when you program, it is important to uh, understand the correct uh, operations that you're performing, and for that natural language is very useful. But when you um, when you convert it into the C programming language or any other programming language, you have to use the correct words, right? And here I had the mistake that I had made is I had used the English word or instead of the operator or. Now let me compile this. And as you can see, the compilation succeeded. There is no main file, and let us just look at the file that has been created. So observe that listmethods.c is the C file that we created, and listmethods.o is the executable that has been created, and it's been created at this particular time, which is Friday, right? A few hours after I should have uploaded the file, but that's okay. I'll upload it in a couple of hours now, right? At this time, right? So this is very recently created, and this object file is created. So let us just take a look at this object file. Okay. Sorry. So as you can see, there seem to be a lot of interesting things that are worthwhile reading. For example, the reason I showed this to you is, okay, these are all some indices, right? And this seems to be some information about some tables, right? And now you can see my function name size is visible here. The function name is empty is visible here. Is first is visible here, and so on and so forth. I did not show you the object file to explain any theory to you, but to show you that there is something curious going on in the object file, and you can actually view it, right? And let me show you the command on a machine, right? It's an octal dump, right? OD stands for octal dump, right? And I want everything to be shown as characters, right? And I am doing an octal dump of listmethods.o, right? Anyway, and if you want to know what octal dump is, you can go to a Linux machine and you can do man od, and it tells you it is an octal decimal hex ASCII dump. Tells you that the OD utility is a filter which displays the specified files or standard input if no files are specified in a user specified format. So you can actually look at files that you typically cannot look at. All right. So where are we now? Right. So we have created the list methods.c. We've compiled it and made an object file. So we have completed creating the abstract data type. We even compiled it, but you should not believe me because I have not shown you how to use it and I have not shown you the proof that it works. Though it did compile, I must show you that it works. To show you that it works, I'm going to take you to my slides first and then show you that it works. I'm going to show you this programming exercise. The programming exercise is extremely simple. Anybody can understand this programming exercise. Okay. Want you to read two positive integers from input that are given on separate lines. We're going to store the digits one after the other from the most significant digit in the left to the least significant digit on the right, in a corresponding linked list. And I want you to compute the digits of the sum into a separate list and print the resulting number. You might think that this is a trivial programming exercise, but it really is not trivial because I did not tell you how large the integers are going to be. You're going to see that we will be able to add integers of arbitrary size. Therefore, when you read the input, you cannot assume that you are reading one integer. So you have to choose a careful data type to read, right? Because none of the basic data types can possibly hold the values that I will give as input. I promise to give inputs which have 200 digits or 100 digits or 50 digits, right? And if I give 50 digits, observe that you are essentially trying to represent numbers which are 10 power 50, right? And you can't represent 10 power 50 in any of your data types, right? So let us see, 10 power 50 is 2 to the power of 150 approximately. It is more than 2 to the power of 150. So you're not going to be able to represent it even in the long integer data type which occupies 8 bytes, right, or 64 bits. So what is my idea? The idea is to solve this particular problem, to be able to deal with arbitrarily large integers and perform arithmetic. I am going to read in the input character by character and enter the digits into a list. Now, of course, I must deal with a situation where meaningless characters are inserted. Right? So let us now observe. The ASCII code for the character corresponding to 0 is 48 and the ASCII code for the character corresponding to 9 is 57. This is a very nice thing and we will use this in our program. So what are the challenges in this exercise? Right? So the challenges are, if the ASCII is specified out of range, then, or if it is not a space or an end of line, we have to print an error message. Right? In this, you will see that we will just return a -1. Because we will go with the programming practice that we have been following, that the output messages will only consist of the specified value, right, and not have any message to the end user. Now, you will recall that the reason I'm doing this is that this way of thinking helps you participate in programming contests, for example, where you understand the input format and print out the output in a certain input format and not always have messages in English saying please enter the input and this is the output and so on. That kind of messages we are going to completely avoid. Right? Therefore, we will not print any error in the output. Right? If there is an error in the input, we will not print an error message, but we will return a value of -1. Okay. As each character is read, we will insert it into the list, and we will use the methods that we have described in the abstract data type. For example, we will use the last method, we will use the before method, and we will use the insert first method repeatedly, right, in a very careful fashion. Right? So for example, as you read inputs from the list, you have to add it, right, to the, remember that the value is typed by you in the is given by you as an input, and the processing of the input happens from the left to right fashion. That is, you see the most significant digit first, then the next most significant digit, all the way down to the least significant digit. Therefore, we will have to insert the numbers, right, right, in the correct order. Right? To set up the addition, we will start identifying the last element of the number and then use the before method and keep adding the values and keeping track of the carries. Okay. So what did I mention here? I just mentioned that we are going to use the abstract data type we have just described to compare, to perform big integer arithmetic. And as an example, we are only going to show big integer summation. When I mean big integer summation, I do not place any restriction on the size of the integer that will be input. Now let's go to the source. Okay. The source is called big add sub.c, right? Big addition and subtraction.c, right? And it will use all the methods in the list methods.c. So now let us go to the C file and look at the implementation. Alright, now the first hash include is the most important. We use list interface.h. Now that you've seen the first hash include, let me quickly exit, compile, and run this program for you so that you get a feeling of what the input and the output look like. GCC -O. Send the output to big add sub I want to compile big add sub.c along with list methods.o. You see this? The object file is now compiled along with this C file, and the compilation is successful. As you can see now, I have created this executable, right, which is big add sub. So now let us execute big add sub. Now let me give a super large integer, let's say 11111, and give as the second integer 9999. Okay, so what should you see? Right, you should see a 1 digit longer number where there is a 1 and everything else is a 0. Sorry, everywhere else there is a 1 and there is the least significant digit is a 0. Okay. So just understand the input. The first 2 lines were the input that I had given. The next 2 lines was printing out the input again, and the third line is a summation. Let's run it again. These are the 2 inputs, right? I have no idea how to read these numbers. It's 1 followed by a large number of zeros followed by a 1 added to as many digits, all of which are 9s. So as you can see, the number is correct. It's 1 1 followed by a large number of zeros, which is the number of digits is 1 more than the total number of digits that were there. So let's do one more input. As you can see, the behavior of the program is highly unpredictable, right, when this happens. And you will see why these dashes and all these things show up. Right? So the behavior of the program is almost, the output is meaningless. Right? So of course I should have caught these errors. Right? And so let us do one more. So this is a meaningful input and we know what the output is. It's 1 more than this very large number involving only 9s. Alright, so essentially what have I done? I've used the list data type to perform big integer arithmetic, or rather to perform addition of 2 very large integers. So in the next 5 or 10 minutes, we will look at the C program that I have done, which makes function calls to this list abstract data type, and then the class will end. So the file, as you know, is called bigaddsub.c. So let us just quickly run through this file. I will also ensure that by the middle of next week, the whole C program is available to you for your exploration. So I have not put in the appropriate remarks. I should have put in the appropriate documentation saying that developed by etc. etc. This is good programming practice, and also describe what the function is, right? But this has not been done. Okay. So now I have 4 functions, right? What it does is the first one checks the meaningfulness of the character value. Okay. The next one is called the num read, which reads a number into the initial list. Right? So what does it do? It takes as an argument a pointer, right? And then reads a value and returns the value that was read. And this is very crucial. It returns a value that was read. The last one is something that prints a whole list in the format that we want it. And sorry, that was not the last one, the penultimate one. The last one is the add function, which takes 2 lists of which encode 2 large integers, adds them and returns a pointer to a new list. Okay, so let us just look at the different parts of the code. Okay. So number 1 is a pointer to the first number, number 2 is a pointer to the second number, num result is a pointer to the result, character is the read val is a character variable to read one value at a time from the input. Okay. So let us just see what happens. Okay. You read the value. Okay. Now you check the value of read value if of the character read, if it is valid, and if it is not the end of line character. Right? Then we create the first node of number 1, okay, and observe this formula. Right? We are using the fact that the number 0 has an ASCII value, or rather the printable character 0 has the ASCII value of 48. Right? And C allows us to subtract an integer value from a character value. So here, this is the character subtracted with 48. It means that the ASCII value of this character is from the ASCII value of this character, the value 48 is subtracted. And then the number is made to the next number pointer, number 1 pointer or next is made to point to null. Now, then you read the next value. Okay. So let us just understand what this function does. Right? This part computed it created a node, right, for the number 1. Now num read, right, is a function which takes a pointer to this list and returns a character. It is the last character that was read before exit from the function call. So let us just understand this. Right? Num read returns the last character read from the input before the function call. So num read does this. Now why do we need this? Is that if the last character that was read was a meaningless value, you just exit. Then we similarly read number 2. I'm going to skip this piece of code, right? Because most of the work, the function calls to the abstract data type happen in the num read function. So I'm going to go directly to the num read function. Okay, now what you do is you print the number list and print the 3 numbers, right? So number 1 is a list, number 2 is a list, and print number underscore result, which contains the sum. And num result is what? It is another list which is obtained by performing an addition on the lists number 1 and number 2. Alright, so now let us just look at this. Okay. So check value is a very simple function. It checks if the character is a meaningful value. Right? So it says if the value that is read is a space, right, then you return a -1. Right? And if it is not a space but some other character, you check if its value is smaller than 48. Right? Or if the value is larger than 57, in that case you return a -1. So we'll just come to this later, right? So this might require a small amount of correction. So I guess the correct thing to write is that if the read value is outside the range 48 and 57, that is, it is not in the interval 48 to 57, that is, the ASCII code is not in the interval 48 to 57, then you return a -1. That means it must be outside this range, that is, it must be either smaller than 48 or larger than 57. Otherwise, you return a -1 saying that the value is valid. Okay, now let us go to the number read function. Right? So observe now that one digit of the number has been read when this function call has been made. This is a very crucial property. When this function call is made, one read of the function is one digit of the number has been read, right? And number is pointing to some meaningful value. So that is, now you read the next character from the input. The while loop now checks whether the value is meaningful. That is, it is neither a end of line nor is it a meaningless value. You create a new node called another node. You put in the corresponding integer value by saying read value -48. Make another node point to null and enter it as the last element of the list. Observe that we have now in this used one of the ADT functions. In the list number, identify the last element and make this new node the last element of that list. Right? You're reading the input from left to right, so therefore every number that you read should go to the last element of the list. Now you read the value, next value, and iterate. Right? So this is essentially the num read function. Now let us look at the print function. The print function is fairly straightforward. Right? It checks if number is null, while as long as number is not null, you print the value, don't give any unnecessary space, and move on to the next number. When you exit from here, print a new line character. Now let's go to the add method. So we are in the last part of this lecture, right, where we are going to use all the features of our ADT that we have developed. Already observe that we have used the last method in the ADT. Right? Last of number returns a pointer to the last element, right, of the list called number, right? And therefore last of number is a pointer. Okay, nice, right? So now let us look at the add function. What are we going to simulate? Right? So the add function is going to simulate the pencil paper method of adding. So this function simulates the paper pencil this function just simulates the paper pencil method of adding that we humans do. Right? So let us look at the variables that we have. We have one pointer called answer, one pointer for new node because we have to create a new list which contains a sum. Okay. And then we have two pointers L1 and L2. L1 and L2 are designed to store the last values, right, in the unprocessed part of the numbers. L1 and L2 are designed to store the last value in the unprocessed part of the two numbers. Right? So L1 is last of N1 to start with. That is, it is the last digit, the rightmost digit of N1. L2 points to the location that has the rightmost digit of N2. Right? Now you create a new node and carry is initialized to 0. Sum is also initialized to 0. Now you say sum is carry plus the value of L1, value in L1 plus value of L2. Now you take the digit by taking the remainder, that is divide sum by 10 and take the remainder. Right? That will be the value that has to go into the new node. This is clear. This is the paper and pencil method. The carry is the value that you have to carry over to the next digit summation. Right? So now this computes the value in the new node. This computes the carry. This carry will be used for the next summation. Right? And make answer point to new node. Now observe that the first digit of the answer list has been created here. Now we go into the loop. Let us just look at what are the three cases in the loop. The three cases in the loop are, right, this loop runs as long as before of L1, N1 is not null, and similarly before of L2, N2. That is, it moves from right to left. The summation, as you know, is happening from right to left. Right? So as long as you have not reached the leftmost digit of either of the two numbers N1 and N2, the control will be inside this loop. So let me repeat this. The implementation happens in a few cases, in 3 cases to be precise. This while loop runs as long as the control has not reached the leftmost digit of either number N1 or the leftmost digit of either number N2. Control keeps running here. If it reaches the leftmost digit of one of the two, then some other action has to be taken. The control exits from the while loop. Okay, let us see what happens. So L1 is now the digit before, right, the current candidate for the leftmost digit. That, remember, we are processing from right to left, right, adding it digit by digit like the paper pencil method. Right? Now here L1 and L2 were the two digits that were processed, pointers to the two digits that were processed in the previous iteration. After the execution of these before functions on the lists N1 and N2, L1 and L2 point to the predecessor of the digits processed in the previous iteration. Right? Okay, now we create a new node to store the sum. Sum is now going to be the carry which came from the previous digit. Right? You take the L1 value and the L2 value, add them up and you get the carry. The least significant digit obtained by taking the remainder on division with 10 tells you what value should be in new node. Then the carry is updated. Okay? And new node is now made the first element of the longer list. New node pointed out next is answer. Right? Okay? Of course, I could have made this function call here equivalently. Let me put this remark. Equivalently, we could have insert before answer, that is in the list answer, before answer, before first of answer, right? Insert new node. Okay. This is exactly what I should have done. That is, insert before in the list answer. And where should you insert? I must insert before the first element of answer, and I will insert new node. Now, when control exits from this while loop, it means that either we have reached the leftmost digit of either n1 or n2. Let us assume here that we have reached the leftmost digit of n1, which means what? n2 has furthermore many more digits to the left than n1. Okay? Therefore, you should now visualize n1 as lot of zeros prefixed, right? And that is all we have to perform. So here what do we do? So till we reach the leftmost digit of n2, what do? We take the leftmost digit of n2, right, and repeatedly add the carry, right, and insert it into the list. Insert the new node into the list, which is answer. On the other hand, if symmetrically, if n2 becomes null, if you reach the leftmost digit of n2, then you repeat this by adding to the digits of n1 the carry iteratively till the whole number is processed. At the end of all this, if you still have a carry, you have to add a new node. This is what happens, right? At the end of all this, if you still have a non-zero carry, right, then you insert it into the list answer, which has your summation finally, and you return a pointer to this newly created list. I hope the add function was clear. The add function basically made function calls to the methods in the abstract data type and created a new list which has the summation of the two given numbers which are represented in the list. Lists number 1 and number 2. Finally, we print the result and exit from the function. So this completes the description of this whole program, and observe that we have used features of the abstract data type extensively in this exercise. So that completes the code walkthrough. Let's get back to our slides. Right? Really, now I can confidently tell you that you're welcome to the world of programming and data structures. And really what we have done today is the course template. What we will do is we will define an abstract data type, we will implement the abstract data type, we will use the abstract data type, and when we meet next week, we will study the array abstract data type. Let us notice, okay, some important features in today's lecture. Right? Observe that the list methods.c was not used by the C file was not used by the programmer who programmed big add sub.c. Right? This person had access only to list interface.h, right? And this was done along with methods. Right? This was compiled along with list methods.o, which is the object file. In particular, I want you to notice that the programmer of big add sub.c cannot see the contents of list methods of c.c, right? Because it is compiled into list methods.o. Of course, I have access to list methods.c. If I wished, I could see them. But as a programming practice, a good programmer or a good system of a group of programmers do not exchange the C files unnecessarily. They only exchange the .o files. Right? So again, for the third time in this course, I'm asking, what is this famous programming approach? Observe that list methods.o is called an object file. All right, so let us end this lecture and let us end the lectures of this week. The programming assignment will be released to you on Sunday evening, right? And observe that the first programming assignment, the deadline has been extended to Monday morning. So sometime on Sunday evening you can look forward, or by Monday afternoon you should be able to look forward to the second programming assignment. Thank you very much.